Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be working on Unit 10, Lesson number 14, Reasoning about Radical and Rational Equations. So, throughout this unit, and in the last one where we worked some with solving equations that involved square roots, we saw things known as extraneous roots. And those were kind of a mystery. Why did they arise? Why did we do everything correct algebraically? And yet, we got values of x that didn't work in our equations. Well, today we're going to justify the steps that we use to solve both rational equations and equations involving square roots, and we're going to try to understand a little bit better about why extraneous roots come about. But let's jump into it a little bit and understand some properties of equality. In order to actually justify both the solving of rational equations and equations involving square roots, we need two properties of equality, the addition property and the multiplication property. And these are pretty straightforward, but it goes something like this. If A equals B and C equals D are both true, well, then A plus C equals B plus D. And for the multiplication property, A times C equals B times D. Now this is pretty obvious because, if 5 is equal to 5 and 3 is equal to 3, well then 5 plus 3 must be 5 plus 3. 8 equals 8 is a true statement. Likewise, 5 times 3 must be equal to 5 times 3. 15 equals 15. So this seems amazingly obvious. If two quantities are equal, if they are truly equal, and another two quantities are truly equal, then you can add them to each other or multiply them by them. You can also divide them and subtract them. You can divide as long as one of them is not equal to 0. All right. Now these are the properties that we're going to use to help us justify our steps in solving equations. So let's take a look at that. In exercise number 1, it says give a reason or cite a property for each of the following lines in the solution of a square root equation. So cite a property or give a reason. So let's say that we're trying to solve this equation. X equals the square root of x plus 6, right? The first step that we typically do is we square both sides. But what does that really mean? It really means that we're taking this equation and, if you will, sort of multiplying it by itself. So that is justified by using that multiplication. That's an interesting I that I have right here. Let me get rid of a little bit of that. It's sort of strange. That's the multiplication property of equality. That's really that one that says, if A equals B and C equals D, then A times C equals B times D. We're really using it here, though, as saying, well, if A equals A and B equals B, then A times A must be equal to B times B, right? So this is my A, and this is my B. So now I have A times A equals B times B. All right, simple enough. And then, of course, what we get is we get this x squared equals x plus 6. The next line that we're going to justify is that we're going to actually subtract x and subtract 6 from both sides. Now, what allows us to do that? Well, that's actually the addition property of equality, right? Because what we're saying is, right, anytime you add the same quantity or subtract the same quantity from both sides, you're using that addition property of equality. That allows us to then write this quadratic equation like that. Then we can factor it. And then we set each factor equal to 0 when we solve. What was that called again? When we set each factor equal to 0 when we solve? That's the zero product law. Now, I want to be very clear. There's a bunch of stuff here that we haven't justified. We haven't justified why x squared minus x minus 6 is x minus 3 times x plus 2. There's actually a lot of different properties that sort of justify why the thing circled here in blue is equal to the thing circled here in blue. So there's a lot of steps in our reasoning here that we really haven't even gotten into. Okay, but the main steps are the multiplication property of equality to get rid of those radicals, then the addition property of equality to get it all equal to 0, and then the zero product law in order to solve for the final roots. But even though we've done everything beautifully here, even though we've used properties of equality and the zero product law, one of those two values of x is extraneous. It's not correct. Pause the video now and figure out which of these two values of x, circled in red, do not solve this equation. All right, by doing a check. Pause the video now and do that. All right, well, really, we should be able to just check it. So let's check it for a minute. All right, let's check x equals 3 first. Right? If I put 3 into that equation, I get 3 equals the square root of 3 plus 6. So 3 equals the square root of 9. 3 equals 3. That checks great. No problem there. But then if I put negative 2 in, I get negative 2 equals the square root of negative 2 plus 6. Negative 2 is equal to the square root of 4. Negative 2 equals 2. No. So that's extraneous. Remember, in this square root, it's only the positive. If we wanted the negative square root, there'd have to be a negative out front. So x equals negative 2 is our extraneous root. Shouldn't be there. But the second part of this question asks, does the extraneous root satisfy this equation? This equation that was produced by using these properties of equality. Well, check it for a minute. See if this checks in this equation. Take a moment. Well, let's take a look. Negative 2 squared equals negative 2 plus 6. Negative 2 squared is 4. Negative 2 plus 6 is 4. So yes. So that's weird. You know, here we've got this value of x that clearly does not solve the original equation, and yet it solves one of the equations that was produced by using properties of equality. Now, that's kind of weird, right? And we're going to talk about why that is in the next part of this presentation, right? And it really all gets down to one simple thing. Squaring both sides of an equation is what's known as an irreversible property. And we'll talk about that in a moment. Pause the video now, though, and write down anything you need to. Okay, I'm going to clear out the text, and let's talk about irreversible processes, or irreversible operations. An irreversible operation is an algebraic manipulation that cannot be uniquely reversed. All right? Now, what do I mean by this? Well, let's play a little mental game here. Let's say I'm thinking of a number in my head, and I add 3 to that number, and I get 10. What number did I have in my head? You catch that? So I have a number in my head, I add 3, the result is 10. What number did I have in my head? And your answer is probably 7. And it's very simple. Addition is a reversible operation. I can just take the 10, I can subtract 3, and I get 7. Now let's try another one. I have a number in my head, and I square it, and I get 25. What number did I have in my head? And your answer should be, well, yeah, you had 5 in your head. Oh, wait a second. Or you had negative 5 in your head. Squaring is an irreversible operation, right? Once you've squared something, you don't know whether what you started with was positive or negative. And that's really at the heart of what's going on here. Let's take a look at how weird things can happen. Take a look at exercise number 3. It says, consider the relatively easy equation negative 2x equals 6. Solve this equation by using the reversible operation of division. Do it quickly. All right. Real simple, right? Negative 2x equals 6. I divide both sides by negative 2, and I get x equals negative 3. And that's it, man. That is the only solution to this. And division is reversible. It is. All right? As long as you divide by something, or multiply by something, you can undo it. Now, remember, I should be able to do any property of equality to this equation, not just the multiplicative property in letter A, where I divided by both sides. Let's actually solve this equation by first squaring both sides. Remember, I mentioned squaring is an irreversible process. Well, when I do negative 2x times negative 2x, I get 4x squared, and then here I get 36. Now let's solve this. Well, let's take the square root of, or let's divide by 4 on both sides, and I get x squared equals 9. But then when I take the square root of both sides, I'm going to get plus or minus 3. So we just introduced an extraneous root of x equals positive 3, right? Positive 3 doesn't solve this equation. And yet, when we squared both sides, all of a sudden it got introduced. Isn't that kind of weird? And again, it goes to the heart that when I square that negative 2x and it becomes 4x squared, for all I know, I could have started off with this equation, right? If I squared both sides of this equation, I'd also get 4x squared equals 36. So it's almost like by squaring both sides of the equation, I could have started off with one of two original equations, and the algebra really doesn't know which. All right? That's why I'm getting that extraneous root. Squaring is irreversible. Pause the video now and write down anything you need to. Okay, let's get rid of it. All right, now let's take a look at a rational equation. Okay, so exercise 4 says consider the rational equation x divided by x minus 1 equals 2x plus 6 divided by x plus 3. It says justify each step of the solution to this equation by citing a property or some other reason. Some steps of algebra have been omitted for the sake of space. Pause the video now and see if you can fill in those blanks. All right. Well, in the first case, what we've done is we've multiplied both sides of this equation by the quantity x minus 1 times x plus 3. Whenever you multiply both sides of an equation by the same thing, or square both sides, you're using the multiplication property of equality. Now, in that case, of course, what happens is that those x minus 1s cancel, those x plus 3s cancel, and you're left with this. In order to solve this, I've got to do some multiplying, so I multiply out that, and I FOIL that out, right, giving me this, and there's many steps of algebra there that could use justification but aren't really the point of this problem. Then I subtract x squared minus 3x from both sides to get it equal to 0. What justifies that? Well, even though I'm subtracting, it's justified by the addition property of equality. Anytime we add or subtract the same thing from both sides of an equation, what justifies that is the addition property of equality. Then we get this, and we factor it, and we set each factor equal to 0, and we get these roots, and that is the zero product law. Now you might say, aren't those the exact same 3 steps that we had in exercise number 1? And my answer would be, why, yes, they are, right? The multiplication property of equality and the addition property of equality are probably 2 of the most important properties that we use to justify procedures that we undergo to solve equations. That was pretty garbled, but hopefully you followed it. Now, of these 2 values of x, one of them is extraneous. Which one is it? And how can you tell? Think about this for a moment. All right, well, the one that's extraneous is x equals negative 3, okay? And it's extraneous because if we substitute it into the equation, this denominator becomes undefined. Well, actually, the denominator is equal to 0, so I'm sorry, the overall fraction is undefined. All right, so it causes a denominator to be equal to 0. Now, again, I want to think about this in terms of reversible operations and irreversible operations. One thing that's happening here, and this is very subtle, it's very tricky to understand this mathematically, is that when we multiply both sides of an equation by an expression involving a variable, like x minus 1 or x plus 3, we could be multiplying by 0. Now, generally, multiplication is reversible, but not when you multiply by 0, right? I mean, if you think about it, let's say I had a number, and I told you I multiplied that number by 0, and I got 0. What number did I start with? Well, there's no way for you to reverse that. You know, if I said, hey, I multiplied some number by 2 and I got 10, what number did I start with? Your answer would be 5. That's reversible. On the other hand, if I say I start with a number and I multiply it by 0 and I get 0, well, you have no idea what number I started with. And that's what's going on here. By multiplying by x minus 1 and x plus 3 on both sides, we're sort of, if you will, accidentally multiplying by 0. That's resulting in a root of x equals negative 3, which is extraneous. All right, well, let's take a look at this a little bit more. Pause the video now, write down anything you need to, and then we'll take a look at this phenomenon one more time. All right, clear out the text. Okay, multiplying both sides of an equation by a variable expression is an irreversible operation because you could be multiplying by 0, which is irreversible. Now, this is really cool. Let's take a look at exercise 6. Consider the very simple linear equation 5x equals 15, whose only solution is x equals 3. And of course, you can get that by dividing both sides by 5. It says solve this equation by first multiplying both sides by x minus 1. What extraneous root has been introduced? Now, if you are saying to yourself, why in the world would I multiply both sides of this equation by x minus 1? That seems a little silly. You're absolutely right. But there's nothing about the properties of inequality that says I can't do it, right? The multiplicative property of equality says I can multiply both sides of this equation by anything I want, including x minus 1. All right, well, let's solve this. Let's distribute that 5x, and it's going to give me 5x squared minus 5x on that side. Let me distribute the 15, and that's going to give me 15x minus 15. Now I think I'll get everything equal to 0 to use the zero product law. So minus 15x plus 15. That'll give me 5x squared, negative 5x, negative 15x is negative 20x, and then plus 15 equals 0. It's all looking good. I could certainly do the zero product law right now, but I think I'll divide both sides by 5 just to make my life a little bit easier. So I'll have x squared minus 4x plus 3. Don't forget to distribute the division, right, to here, to here, to here. And now factor, and I'll get x minus 3, x minus 1. I'll get x equals 3 and x equals 1. Now we know that the only legitimate answer is 3. Clearly, if I took x equals 1 and I plugged it into here, it wouldn't be correct, right? I'd get 5 equals 15, and that's a big fat no, right? But x equals 1 is being introduced as an extraneous root because really what that means is I'm multiplying both sides by 0. X minus 1 is equal to 0 when x is equal to 1. All right. So in both rational equations, this wasn't a rational equation, and square root equations, extraneous roots are being introduced because we are doing a process which really can't be reversed. All right. In one case, it's squaring, and in another case, it's very, very subtly multiplying both sides by the number 0. All right. Well, pause the video, write down anything you need to, then we'll wrap up this lesson. Okay, let's do it. All right, today's lesson was actually pretty deep. Really, the theory behind solving equations all is about manipulating the properties of real numbers and the zero product law in order to find values of x that really solve every step of the equation, that you can kind of work backwards. They solve this, therefore they solve this, and this, and this, and this, and this. But when a process becomes irreversible, like squaring or multiplying both sides by a variable expression, you can easily then have values of x that solve later portions of the problem, but don't solve earlier steps. And therein lies the problem, because ultimately a value of x is only a solution to the equation if it solves the very first step in the equation, which is the equation itself. All right, sounded a little bit confusing. I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.